If you've ever tried to reconstruct a 3D human avatar from a real-world video clip, you know the core frustration. In the wild, footage isn't clean studio capture. It's heavily cropped, partially occluded, or only shows a person's head and shoulders. Yet, almost every state-of-the-art 3D Gaussian avatar method silently assumes full-body visibility throughout the entire training sequence. When that assumption breaks, the optimization goes unstable. Unseen limbs get hallucinated, gradients propagate into empty space, and even the visible regions start to drift and artifact. Today, we're breaking down FlexiAvatar, a new framework that solves this exact problem by making the reconstruction pipeline explicitly aware of body visibility. It's a unified system that handles full body, upper body, and head-only inputs in a single pass, while actually reducing memory and compute overhead. Let's walk through the technical architecture. To understand why this matters, we need to look at the current pipeline limitations. Classical parametric models like SMPL-X give us a strong prior for articulated bodies, but they're locked into fixed topologies and struggle with fine-grained texture. Neural radiance fields improved visual realism, but were too slow for real-time animation. Then came 3D Gaussian Splatting, which brought real-time rendering and high fidelity to dynamic scenes. Methods like GART, Gaussian Avatar, and XAvatar push the state-of-the-art, but they all share a critical flaw. They optimize Gaussians across the entire SMPL-X surface regardless of what's actually visible in the frame. In a head-only video, the optimizer is still trying to fit Gaussians for legs that never appear. This creates ghost geometry, texture drift, and spurious gradients that corrupt the shared representation. Localized methods like Instaji or Guava fix this for specific crops, but they force you to maintain completely separate, purpose-built pipelines. FlexiAvatar unifies this spectrum by restricting optimization strictly to observed regions. The pipeline begins with accurate, visibility-aware body registration. Standard pose estimators fail hard when large portions of the body are out of frame. FlexiAvatar introduces a confidence-weighted keypoint masking strategy. It extracts initial SMPL-X parameters and 2D keypoints, then applies a binary visibility mask that zeroes out low confidence or occluded joints below a threshold, empirically set to 0.4. This ensures the reprojection loss only supervises well-localized, visible joints. To capture subject-specific geometry, it optimizes learnable joint offsets and facial vertex offsets, aligning the SMPL-X face region to a DCA-initialized flame template using vertex, Laplacian, and edge length losses. This yields a personalized, identity-preserving canonical template that remains stable under severe cropping. Next, the method tackles the unseen regions. If you only have a head-only video, the back of the head and shoulders are completely missing. Instead of letting the optimizer hallucinate, FlexiAvatar uses a diffusion-based video generator, specifically MimicMotion, to synthesize auxiliary multi-view sequences. For full-body inputs, it generates a 360-degree rotation. For partial inputs, it uses a full-body then-crop strategy to maintain generative stability while matching the visibility constraints. These synthetic frames are downweighted in the reconstruction loss to prevent diffusion artifacts from overriding ground truth evidence, but they provide crucial texture priors for unobserved areas. Now we get to the core representation. FlexiAvatar uses a hybrid mesh-Gaussian approach. The canonical SMPL-X mesh is upsampled, and each vertex is associated with a 3D Gaussian asset. Identity and animation are encoded through a learnable triplane field. Canonical vertex positions are projected onto the three planes, and bilinear interpolation yields per vertex features. Two distinct MLP groups decode these features. The first predicts pose-independent parameters, static vertex offsets, scales, and color logits. The second is pose-dependent, mapping vertex features and body pose to dynamic geometry, scale, and color offsets. This disentanglement is critical. It lets the model learn stable identity features while handling articulation separately, which is especially important when pose diversity is limited in partial view videos. This brings us to the core innovation, visibility-aware optimization. Instead of treating all Gaussians equally, the method tracks per Gaussian visibility cues directly from the rasterizer. After each frame, it computes a visibility score for every Gaussian based on how often it contributes to rendered pixels. The first 2,000 iterations run a warm-up phase to stabilize coarse geometry and color. After that, it applies Otsu's method to the bimodal distribution of visibility scores to automatically find an optimal threshold. Gaussians falling below this threshold are pruned from both the forward rasterization pass and the loss computation. This is a fundamental architectural shift. By masking invisible Gaussians in the reconstruction and regularization losses, the method completely suppresses spurious gradient propagation from the shared triplane field. Gradients from visible pixels can no longer corrupt unseen regions, and you get a direct reduction in memory and compute proportional to the occluded body parts. Global Gaussian representations still struggle with high-frequency details like facial microexpressions or finger creases. FlexiAvatar addresses this with lightweight, part-specific residual MLPs. These networks take the positional encoding of the Gaussian center, frame index, and body pose, and predict a color residual. Crucially, there are 3 separate MLPs for the face, left hand, and right hand, and they're only activated when those regions are visible according to the visibility mask. The final color is a sum of the triplane color, pose-dependent color, and this residual offset. Ablation studies confirm that restricting refinement to these high-frequency zones is optimal. Extending it to the full torso actually degrades perceptual quality because the base triplane representation already has sufficient capacity for lower-frequency body geometry. For animation, the pose geometry is skinned using standard SMPL-X linear blend skinning. The training objective is a weighted combination of L1, SSIM, and LPIPS reconstruction losses, plus a dedicated facial consistency loss that supervises a differentiable mesh renderer to prevent expression drift. Regularization terms like Laplacian smoothness are also applied in a visibility-aware manner, ensuring we don't oversmooth or undersmooth based on observation density. The results across benchmarks are consistent. On full-body datasets like Newman and ZJ-UMOCAP, FlexiAvatar pushes PSNR and SSIM higher while significantly lowering LPIPS, largely thanks to the residual refinement and robust registration. On partial view datasets like TalkShow and INSDA, the visibility-aware optimization shines. It outperforms methods that assume full visibility by a wide margin because it stops fighting unobserved geometry. The efficiency gains are equally impressive. For head-only reconstruction, the method prunes nearly 50% of the Gaussians, cutting asset memory in half and boosting rendering FPS by over 30% compared to full-body baselines. Ablations confirm that every component matters. Removing the SMPL-X optimization leads to the largest performance drop due to pose misalignment. Disabling visibility masking reintroduces ghost artifacts, and skipping the generated auxiliary views causes texture collapse in unseen regions. FlexiAvatar represents a necessary shift in how we approach 3D human reconstruction. By explicitly respecting visibility constraints, decoupling identity from articulation, and leveraging targeted refinement, it delivers a unified pipeline that actually works with real-world video data rather than forcing it into a studio camera mold. The framework is efficient, robust, and sets a new baseline for partial view avatar generation. The next frontier, as the authors note, will be extending this visibility-aware formulation to handle non-rigid clothing dynamics, which remains the final hurdle for fully generalizable avatars. If you're working on neural rendering, human avatars, or real-time graphics, this paper is a must-read. The code and project page are linked in the description. Let me know in the comments which part of the pipeline you think will have the biggest impact on real-time rendering. And don't forget to subscribe for more deep dives into cutting-edge AI research.